Imagine hopping into a machine, pressing a button, and suddenly finding yourself in ancient Egypt or a distant future where humanity has colonized the stars. Or imagine a device that could propel you forward into the distant future, where flying cars and interstellar travel are commonplace, and humanity has unlocked secrets we can barely dream of today. The concept of time travel isn't just a fantasy, it's a deep yearning to connect with our past and glimpse our future. Time travel has captured human imagination for centuries, from ancient myths to modern movies like Back to the Future and Interstellar. But beyond the stories and the fiction, is it possible? Could science one day allow us to move through time as easily as we walk through space? And if so, how would it work? From Einstein's groundbreaking theories of relativity to the mind-bending possibilities of wormholes and quantum mechanics, time travel is more than a wild idea. It's a doorway into the very nature of reality. But how close are we to unlocking it? And what challenges stand in our way? Before we explore time travel, we need to ask, what is time? Time isn't something we can touch or see, but we feel its effects everywhere. It's the dimension that keeps events ordered: past, present, future. But unlike the three dimensions of space, which allow us to move freely, time appears to flow in one direction, an unstoppable current that carries us forward. Why is that? And does it have to be that way? Time is deeply connected to motion and change. Think of an apple falling from a tree. Without time, we couldn't perceive its journey from the branch to the ground. Time provides the framework that lets us understand cause and effect, one thing leading to another. But what is this flow of time? Is it a fundamental property of the universe? Or could it be an illusion created by the way our brains perceive change? These questions have baffled philosophers and scientists for centuries. In physics, time is often treated as the fourth dimension, alongside the three spatial dimensions: length, width, and height. Together, these four dimensions form what's called space-time, a concept introduced by Albert Einstein. Einstein showed that time isn't rigid. It's not the same for everyone, everywhere. Instead, time can stretch and compress, depending on factors like motion and gravity. This means time isn't a universal constant. It's relative. But what does that actually mean? Imagine two astronauts. One stays on Earth, while the other boards a spaceship traveling close to the speed of light. According to Einstein's theory of special relativity, time for the astronaut on the spaceship would pass more slowly compared to the one on Earth. This isn't science fiction. It's a measurable phenomenon called time dilation. And if you are interested, you can watch its full video on the channel. Similarly, in general relativity, massive objects like planets and stars can warp space-time, causing time to slow down near them. A clock on the surface of the Earth ticks ever so slightly slower than a clock on a satellite orbiting high above. We rely on this understanding to keep technologies like GPS working accurately. Another puzzling aspect of time is its arrow. Why does it only move forward? In the everyday world, we see this in irreversible events. A teacup shatters, but never unshatters, and we grow older, but never younger. This one-way flow is tied to the second law of thermodynamics, which states that the universe tends toward increasing disorder or entropy. But could this arrow of time ever be reversed? Could we find a way to step back through time and reassemble the shattered teacup? To answer that, we have to go deeper into the fabric of reality itself. As we journey deeper into this mystery, keep in mind that time is more than just a ticking clock. It's the very essence of existence. In the early 20th century, Albert Einstein revolutionized our understanding of time with his theories of special and general relativity. According to Einstein, time isn't a constant. It's flexible, like a fabric that can stretch, twist, and bend. Let's break this down. Special relativity tells us that time slows down for objects moving close to the speed of light. Imagine traveling in a spaceship at near light speed. For you, only a few years might pass, but back on Earth, decades or even centuries could go by. In essence, you've traveled into the future. General relativity takes this further, showing how massive objects like stars and black holes can warp space-time. This means gravity can affect the flow of time. Near a massive black hole, time slows down dramatically compared to Earth. Think of the movie Interstellar. It's not just Hollywood fantasy, it's based on real science. So traveling to the future isn't just possible, it's already happening. Astronauts aboard the International Space Station, moving at high speeds, experience time slightly slower than we do on Earth. When they return, they've aged a tiny bit less, a real-life example of time dilation. Now imagine scaling this up. If we could build a spacecraft capable of approaching light speed, we could travel thousands of years into the future in just a few years of our own time. But the catch is, we can't come back. And that brings us to the real challenge, traveling to the past. Traveling to the past is far more complicated and controversial. Einstein's equations suggest it might be possible under certain conditions. One theoretical method involves wormholes. Wormholes are shortcuts in space-time, connecting two distant points like a tunnel through a mountain. If one end of the wormhole experiences time dilation, it could theoretically create a time difference between the two ends. Step through one side, and you could emerge in the past or future. But here's the catch. Wormholes are purely theoretical, and even if they exist, they'd be incredibly unstable and likely collapse instantly. Another concept is the closed time-like curve, proposed by physicist Kurt Gödel. This idea suggests a spinning universe might allow paths through time to loop back on themselves. However, this idea remains speculative and unproven. But even if time travel to the past were possible, it comes with a host of paradoxes. Take the famous grandfather paradox. If you traveled back in time and prevented your grandfather from meeting your grandmother, would you even exist to go back in time in the first place? Physicists have debated ways around these paradoxes. One theory is the many worlds interpretation, which suggests that traveling to the past creates a new, parallel timeline. In this scenario, any changes you make don't affect your original timeline. They create a new one. Another idea is that the universe simply prevents paradoxes from occurring, enforcing a kind of cosmic self-consistency. Based on what we know, time travel to the future is scientifically possible, though extremely challenging to achieve at large scales. Time travel to the past remains speculative, limited by paradoxes, and reliant on concepts like wormholes, which are far from proven. The idea of bending time to revisit cherished memories or glimpse the future taps into something deeply human: our curiosity, our nostalgia, and our desire to understand our place in the cosmos. Whether time travel becomes a reality or remains a dream, it inspires us to push the boundaries of what's possible. If you enjoyed this journey through time, don't forget to like, share, and subscribe.